right, so in our next problem, it says each year students in an elementary school take a standardized math test at the end of the school year. For a class of fourth graders, the average score was 55.1 with a standard deviation of 12.3. These same students in the third grade, right, these same students had an average score of 61.7 with a standard deviation of 14. The correlation between the two sets of scores is 0.95, so very high correlation, because remember the highest it can be is just positive 1. The lowest it can be is negative 1. So we now are going to calculate the equation of the least squares regression line for predicting a fourth grade score from that student's third grade score. All right, so I've put all of that information kind of outlined right here, the information for students when they're in third grade, the information for those same students when they're in fourth grade, and here's that strong positive correlation of 0.95, meaning students that scored very highly in third grade, all right, at the top of their class in third grade, tend to score at the top of their class in fourth grade. Those scoring at the bottom of their class in third grade tend to also score at the bottom of their class in fourth grade, and so on. So here's our basic regression equation skeleton. We have our y hat is equal to a plus b times x. A is going to be our y-intercept, so we need to calculate what our y-intercept is, and b is going to be our slope. We need to calculate our slope. The first of these two we can find out is going to be b, our slope. So our slope is just going to be equal to r, which is the correlation, times the standard deviation of the y variable divided by the standard deviation of the x variable. Remember, we're using third grade scores to predict fourth grade scores. And so the third grade information is going to be of our x variable. Fourth grade information is going to be for our y variable. So when we're doing this, right, it's going to be 0.95, that's our correlation, times the standard deviation of the y variable, 12.3, divided by the standard deviation of the x variable, 14, to give us a slope of positive 0.835. Now that we have the slope, and we're ultimately just going to plug this in right here, so we know that it's going to be y hat is equal to a plus 0.835 times x. All right, but once we have this slope, we can now calculate what the y-intercept is going to be. All right, the y-intercept is going to be equal to the average score of the y variable, the average fourth grade score, minus b, which is our slope, times the average score on the x variable. Okay, so that's simply just going to be 55.1 minus our slope, 0.835, times the average of the third graders, 61.7. All right, and so that gives us a y-intercept of 3.581. Right, and so at this point, we can just plug in these values to get our regression equation, being y is equal to 3.581 times 0.835, that's our slope, times the score made in third grade. So a student's predicted fourth grade score on that math test is equal to 3.581 plus 0.835 times the score they made on that math test when they were in third grade. Biologists assess how closely related similar species are by measuring the number of years since the two species diverged from a common ancestor. Researchers Daniel Bolnick and Thomas Neer compared the years since divergence for 12 different pairs of sunfish species to the hatching success of eggs produced by a cross between the two species. A scatter plot of the results is shown. A hatching success of 100 means the hybrid eggs hatched as often as the single species eggs hatched. A number below 100 means the hybrid eggs hatch less often. Okay, so we really don't even need to have any grasp at all of what they are saying. If you have no idea what any of that means, no problem. And the reason is that they give us this scatter plot, and all we have to know is by looking at this scatter plot how strong the correlation is between our two variables. And we can see that we have, one, it's going to be a negative correlation, and two, it's a pretty strong negative correlation. They're pretty much, all these dots are pretty much along this line, except, these two diverge a little bit. But it's a pretty strong negative correlation, so the answer is going to be A, and it's as simple as that. Okay, so in this next problem, we're asked which of the following statements is not true of the correlation R between the length in inches and weight in pounds of a sample of brook trout. All right, so you get a bunch of trout that you've collected. Is there some kind of correlation between the length of the trout and the weight of those trout? And we're looking for which one of these four statements isn't true. So the first one says R, or the correlation must take a value between -1 and +1. That is true. Let's look at C. If longer trout tend to also be heavier, then R is greater than 0. That one's also true. You have a positive correlation, or a positive R. Here, hold on a second. Right? You have a positive correlation or a positive R. In other words, an R that's greater than 0. If as one variable increases, so does the other. Okay, so that's what's going on here. Trout with a greater or a higher length tend to also have a greater weight. So as length increases, so does weight. So that would be a positive correlation. All right, and D is also going to be true. R would not change if we measured the lengths of the trout in centimeters instead of inches. That is true. Correlation does not care about what unit of measurement you're using. All right, so A, C, and D are all true. What's false is B. Correlation is not measured in inches. So B is what is not true. Okay, so it says the scatter plot shows the relationship between life expectancy in years and internet users. All right, how many per 100 individuals in the population? For 35 countries in North and South America, along with the least squares regression line. Haiti had a life expectancy of 45 years and 8.37 internet users per 100 people. What effect would removing this point have on the regression line? Okay, so this is Haiti right here. Life expectancy of 45 and a 8.37 internet users per 100. So we can clearly see that Haiti right here is an outlier. It's very far off from the line that fits pretty well the rest of the data points. So what this data point's doing to the line currently is it's pulling the slope downward. All right, if it weren't for Haiti, the slope would be more of a flat line than it currently is. But Haiti's pulling that line down to make it more of a positive slope than it would be otherwise. So if we get rid of Haiti, what's going to happen is this slope, which is positive, it's going to decrease. The slope is going to decrease. So we know that it's going to be either C or D. And then what's going to happen when the slope decreases? It's the y-intercept is going to kind of increase. So it's going to look more like this. So the y-intercept will increase and the slope is going to decrease. So that's going to be answer choice C. In a certain population, there's an approximately linear relationship between Y, the height of females in centimeters, and X, their age in years from 5 to 18. Right? And that linear relationship is described by the equation of predicted height is equal to 50.3 plus 6.1 times age. Age is the x variable. So which one of the following statements must be true? All right, so let's look at A. It says that the estimated slope is 6.1. That's true. 6.1 is the slope. 50.3 is the y-intercept. And this implies that girls in this population between the ages of 5 and 18 are predicted to grow about 6.1 centimeters in height for each year they grow older. That is correct. All right, answer choice A is the correct answer. There's going to be something wrong with each one of these other answer choices, but A is correct. All right, in 7, there is a positive correlation between, hold on one second, there's a positive correlation between the size of a hospital, measured by number of beds, and the median number of days that patients remain in the hospital. Remember, median is kind of like average. Average is equal to the total number of to the sum of the scores divided by the number of scores. The median, on the other hand, is that middle score, the score that's in the middle after you have ranked the scores from least to greatest. All right, so positive correlation between size of a hospital and the median number of days. So what does that mean? In larger hospitals, patients tend to spend a larger number of days in the hospital. All right, if you go, patients at smaller hospitals tend to stay at that hospital for a shorter period of time. At a larger hospital, a greater period of time. So does this mean that you can shorten a hospital stay by choosing to go to a small hospital? All right, so the answer is no. The simple reason is because correlation does not imply causation, meaning we don't know if the size of a hospital actually has a causal effect on the number of days people stay at the hospital. There might just be a correlation but no causal connection. We know that the answer is going to be either A or B. All right, because correlation does not imply causation. A is going to be incorrect because it says a negative correlation. So we had a positive correlation, but it says a negative correlation would allow that conclusion. That's not true either. No correlation will allow for us to draw a causal inference. So that's why B is correct, because B actually gives a possible explanation for why there's this correlation. It says perhaps the positive correlation arises because it just so happens that seriously ill people tend to go to larger hospitals. Perhaps they feel safer or more secure going to larger, more established hospitals. And what do seriously ill people tend to do? They tend to spend a lot of time in the hospital. And so they're pulling up that median number of days. Okay, so that's why B is going to be the correct answer for number 7.